have Dr. Justin Thompson, and he's going to be talking about exploring groundwater recoverability. And let me just tell you a little bit about Justin. Justin very recently received his PhD from the Jackson School of Geoscience at UT Austin in December of 2021. And his dissertation research focused on groundwater recoverability and management in Texas, and he served as a graduate research assistant at the UT Bureau of Economic Geology for over 3 years. Justin holds a Master's of Science in Energy and Earth Resources from the UT also, a Master's of Global Policy Studies from the UT LBJ School, and a Bachelor of Business Administration and International Business from Texas Tech. And Dr. Thompson has an international project development and finance professional for the last 12 years prior to his graduate studies. He is proficient in Mandarin Chinese and has an extensive experience with nonprofits bringing groundwater and rainwater solutions to underserved communities in East Africa. Wow, what a bio.
Thank you.
Well, thank you so much for joining us. And without further ado, take it away, Justin.
All right, perfect. Well, let me echo Heather by saying thanks everybody for being here, for spending your lunch hour with us today. So again, I'm Justin Thompson, and today I'm going to talk to you about research conducted in pursuit of my PhD at UT Austin, entitled Exploring Groundwater Recoverability. So let's jump in. So first, let's talk about motivation. Why did we conduct this study? Well, groundwater in Texas is managed on the basis of desired future conditions. And desired future conditions are essentially a statement of what do we want our aquifer to look like over a planning horizon. They take many forms, everything from saturated thickness metrics to spring flow minimums, but they're most frequently expressed as a depth to water change over time. So something like, say, 50 feet of drawdown over 50 years. Our regulatory entities that adopt desired future conditions are required by law to consider sort of a checklist of items when they adopt those conditions. And that's what we have pictured here. It's sort of a range of things, some of which are perhaps at loggerheads with one another, but they're supposed to all be considered, and they include things like the feasibility of achieving the desired future condition, water supply needs and management strategies, environmental impacts like, say, the spring flows we have pictured here on the right, all the way down to a few things that we're particularly interested in here today, right, such as hydrologic conditions, recharge into and discharge out of the aquifer, and this term called total estimated recoverable storage, as well as the socioeconomic impacts that are reasonably expected to occur as a result of the desired future condition. So let's look at these last two that we're interested in here today in a little bit more detail. First, total estimated recoverable storage. Well, what is it? Well, it's Texas' best estimate of groundwater recoverability. It's two numbers. It's 25% and 75% of total storage. Total storage, in turn, is a statutorily defined term, and it really means the total volume that an aquifer is capable of producing. Okay, well, how do we arrive at that number? Well, let's visualize it real quick. We've got here pictured here on the right two different aquifers, an unconfined aquifer on the left and a confined aquifer on the right. And this image is taken directly from board TERS, total estimated recoverable storage. I'm going to call it TERS. This image is taken directly from TERS reports. So to come up with total storage, what we're doing here on the left in an unconfined setting is we're imagining the water level today, and we're saying, okay, well, what happens if we drain that water level all the way to the bottom of the aquifer? How much water would be produced? Well, that calculation is pretty easy. It's pretty simple. It's right here. It's the storage area, the land surface area that you're interested in. That might be, for example, groundwater district, right? Multiplied by the depth to water change for total storage. That's, everything from what it is today to the bottom of the aquifer, multiplied by the relevant storage coefficient. In an unconfined setting, that storage coefficient would be specific yield, which might be, say, 0.15 or maybe 0.1. The calculation in a confined setting is similar, it's just kind of got one extra step. You're also imagining that all of the water from the pore space storage is drained, right? So same thing as the unconfined setting, but you're also doing this extra step of deciding how much water would be generated by draining the pressure head, right, from the confined setting. So you imagine the water level today drained to the top of the aquifer, how much water is produced there. It's the same calculation, but instead of a specific yield, you're going to use a storativity number. And that number might be orders of magnitude smaller than the specific yield, right? So if a specific yield could be, say, 0.15, storativity could be 0.0003, for example. And so why is this important? Well, we'll see a little bit more in detail later, but what it really means for now is that the volume produced by draining this confined pressure head is orders of magnitude smaller than the volume produced from draining this pore space storage. So, okay, so now that we know how much water could be produced if we drain this aquifer, whatever setting it might be in, completely, TERS, or total estimated recoverable storage, is that number times 25% and 75%. Well, when you look at the TERS reports, they indicate that there are potentially billions with a B of acre-feet recoverable in the state of Texas. For example, the Carrizo-Wilcox aquifer alone, at just the 25% benchmark of TERS, would give you 1.3 billion acre-feet of recoverable water. So, wow, that's a lot of water, especially when you think about, for example, the latest state water plan, which projects deficits under drought of record conditions of only 7 million with an M acre-feet. So does that mean we have just, gobs and gobs of water that's recoverable in Texas? Well, maybe, maybe not. TERS is a limited metric, right? And it does not consider a few key constraints on groundwater recoverability. It doesn't consider water quality. It doesn't consider pumping dynamics, so how the water level behaves in this well when you pump it. And it doesn't consider the economic feasibility of retrieving that water, of pumping it. Now on to that second DFC consideration that we're interested in here today, the socioeconomic impacts of those desired future conditions. Those are currently wholly unquantified. Why? Well, according to DFC explanatory reports, there is no standardized local or regional socioeconomic analytical tool developed. So how are our groundwater districts and management areas approaching this issue? Well, they use a qualitative method. That includes things like public commentary, right, where their stakeholders can weigh in. These explanatory reports famously include an analysis of the cost of not meeting the water demand, and they pull that from the Texas Water Development Board studies for groundwater planning. But it's widely understood and accepted that that's not really the same thing as the socioeconomic impact of a desired future condition. So this leaves us with some questions that we're going to explore today. Question number one, how could recoverability be better quantified? How could we perhaps take into account some of those factors that TERS does not consider? Number two, how do groundwater storage conditions drive recoverability? Is there a significant difference from one storage state to another? And number three, how might changes in recoverability impact our groundwater users, right? What are those socioeconomic impacts of these desired future conditions? So those are the questions we'll explore. Let's get into it. Let's talk first about our approach. Answering that first question, how could groundwater recoverability be better quantified? Well, let's start with one of those things that total estimated recoverable storage doesn't consider, those pumping dynamics. How does a well respond to being pumped? So as a well is pumped, the water level in the well changes over that pumping period. It's not the same. The water level in the well is not the same thing as the initial depth to water, the driving head, right? There's going to be some pumping drawdown. So the water level in the well is going to change. And that change is impacted by a number of factors. But when we consider that change, how the water level in the well is behaving, what we can do is we can imagine and say, well, there's got to be some water level, right, some depth to water, where that depth to water plus the drawdown experienced at the well over a pumping period is equivalent to the top of our well screen, or alternatively, the depth of the pump itself. And that's what we're imagining is our limit here to the physical recoverability of any given well and aquifer. Why do we consider that a limit? Well, because of this thing called overpumping. It's technically possible to draw that water level down in your well below the top of your well screen or your pump. And we've all actually experienced this when you're drinking your tea or your water or your soda with ice and you have a straw and you get down toward the bottom and you hear that bubbling, slurping sound. That's overpumping, right? It's a lot harder to drink your beverage than it was when the cup was mostly full. So what we see with overpumping is while it's possible, it may damage your well, and it certainly creates some efficiency losses. So if we want to take this pumping drawdown, how water levels in a well behave into consideration, how could we do that? Well, there's a couple of different ways. First, we could look at a specific capacity solution, which is a widely reported number. It might come to you in the form of, say, for example, feet of drawdown per gallon per minute of pumping. And that's useful. You can use that as kind of a quick back of the envelope calculation. You can do it with just a piece of paper and a calculator, for example. But specific capacity has some limitations, right? And we use that in our first paper published in the Texas Water Journal. But it has some limitations. One, it doesn't take into account any of the time-dependent functions of how water levels change in a well over your pumping period. And two, it's tied to a specific well infrastructure. So in our more recent studies, we use different solutions for estimating how water levels behave in the well, starting with, for example, the Tice drawdown solution, which I have written out here. And I don't have these equations written out, in gory detail just to make me look smart. I want to point out a couple of things, right? So one, here's our little r, right, our radius of measure, and we're measuring that just outside of the well, right, to really get an idea of how water levels at the well are behaving. And then more importantly, I've got these T's highlighted. Why do I have these T's highlighted? Well, T stands for transmissivity. And transmissivity is it's an expression of the aquifer's ability to transmit water to the well. And it is a function in part of the depth to water, of the saturated thickness in the aquifer. So what this means is, as your depth to water increases in an unconfined setting, your transmissivity is going to decrease. So what that means is that your drawdown is actually going to increase. So putting that all together, what that means is as your depth to water increases, your capacity of your aquifer and your well to meet your pumping demand actually decreases, right? And that takes two forms. One, that pumping drawdown gets bigger, which we kind of have pictured here, right? This bigger arc than up here. And additionally, the amount of potentiometric head you have available to support this pumping drawdown is going to decrease. And that latter point is relevant in either a unconfined or confined setting. We also, when we think about how the water level behaves and how it changes with pumping and changes in depth to water at the well, we also want to think about partially penetrating well effects, right? So the Tice solution we just showed you assumes that the aquifer is fully penetrated, meaning that the well screen runs the entire length of the saturated thickness in the aquifer. That, might be reasonable in an unconfined setting, confined setting, maybe, but it's certainly not relevant in an unconfined setting. So we want to think about this. Why? Well, let's see down here, when you take partial penetration drawdown considerations into effect, you see that the amount of drawdown you would expect in a well greatly increases over what you might expect if you don't consider it. In this simple example, the amount of drawdown expected without considering it is 3 or 4 times smaller than what you expect when you do consider it. And so here I have the hand 2 solution for partially penetrating drawdown written out. Why? Again, not to make me look smart, but to point out we've got some key coefficients, right, of this solution that are going to change with a change in depth to water or a change in the well infrastructure itself. Now, by incorporating these partially penetrating well effects, this allows us to do 2 important things for this study. It allows us to optimize our well infrastructure. That allows us to answer the question, 1, how much water could be recoverable if a well were optimized to maximize a yield, or 2, how much water is recoverable if pumping costs are optimized to be minimized. And we'll kind of come back to that in a minute. But partially penetrating well effects and modeling those in this study really allows us to answer those 2 questions. So we talked briefly about how we can quantify and incorporate pumping dynamics. Now let's talk briefly about how we can incorporate the economic feasibility of pumping the water. So here what we're imagining is we're saying, okay, well, at some depth to water, there is a point where the cost of pumping the water is going to be equal to or greater than what we're willing to pay for the water. And that's what we're imagining our limit as. Pumping costs, we consider three different components. We consider the lifting cost, so that's the energy cost of lifting the water to land surface, right, from whatever the water level in the well might be. We've got the equipment costs of the well, so that's actually the pump powerhouse. And then we've got the drilling costs. And we express these all on a dollars per volume basis. And here's how we're calculating them. Again, I've kind of got them written out just to show you a couple of important pieces of these equations that are going to change as depth to water changes, right? So lifting cost, this is an energy component, right, based on depth, which is a horsepower converted to electricity, and then using a price, we can come up with dollars. We've got that depth to water, right, whatever it might be, plus that S drawdown, right? So that's going to change as our depth to water increases. Same thing with our equipment costs, right? And then also our drilling costs, simply put, you know, as you're talking about a deeper and deeper formation, you've got greater and greater costs. So the key takeaway here, where in the pumping dynamics part was that capacity falls with increasing depth to water. For economics, the pumping costs are going to rise with increasing depth to water in all situations. Okay, so let's put all this together, right? So on the one hand, we've got the pumping dynamics, right? The aquifer and the well capacity to meet your pumping demand. And on the economic side, your pumping cost versus your willingness to pay. When we put all this together, we can apportion the aquifer into sort of various zones, right? And let's walk through that one step at a time. From the bottom to the top, first we've got our well screen dead pool. So this is the part of the aquifer, the saturated thickness specifically, that's reserved to support our well screen, right? We can't pump that without over pumping. Then above that, we have potentiometric head that's reserved to support our drawdown, right? How that water level is going to respond to pumping in the well itself. And we're calling that our drawdown dead pool. You can't really produce that potentiometric head without inducing over pumping. Then above that, what we have pictured here is a hypothetical situation where the cost of pumping the water equals your willingness to pay at some point above that capacity limit, right? So we've got an economic limit depth to water that's shallower than our capacity limit depth to water. In that case, we have a new zone created called the economic dead pool. So this is potentiometric head that is feasible to produce under physical limitations, but infeasible to produce under economic limitations. Everything between the current water level today and these two limits is feasible production. We're calling that the production range. So what we can do is we can go back to that yield calculation provided to us by total estimated recoverable storage and evaluate that change in depth to water between what it might be today and these limits to come up with a yield number. So how are we doing that? How do we put all this together, practically speaking? Well, of course, like good scientists, we built a model. A model that we call the groundwater recoverability model. I know, very creative. What does the groundwater recoverability model do? Well, it quantifies changes in recoverability, right, with changes in depth to water. It can also optimize well designs for us, either to maximize recoverable yields or to minimize recovery costs. And it can also quantify those socioeconomic impacts that we would expect with the change in water driven by a desired future condition. Rather than put a bunch of, pretty Python code on the screen for you to sort of describe this model, what I've done here is do my best to kind of visualize it for you. So the groundwater recoverability model, first it intakes some parameters from the user. First, we've got some user-specific values, your demand, your pumping time, how much are you willing to pay, what are your relevant prices, what's the storage area producing the yield, right? Oh, and this approach, we're looking at either a hypothetical or an existing well. You can do either one. And this is how the model calculates a yield. right? So you've got your user values. Then we've got some well values. What's the efficiency of your well? If it's an existing well, what's the depth of the pump? What's the depth of the well bore intervals and the screen? And then finally, we've got some aquifer parameters. And I've got these highlighted in red for you here today because these parameters are actually coming to us from the board's groundwater availability models. All right, so we've got aquifer geometry, right? What's the depth of the bottom of the aquifer? How thick is it? What's the hydraulic conductivity? And then also what's the depth to water, that initial starting depth to water. So the groundwater recoverability model takes all of these inputs and puts them together and calculates quite a lot of things for us. It takes well losses into account. It calculates artesian flow if that's relevant, and all together comes up with a pumping rate. We look at changes in transmissivity with changes in depth to water if that's relevant, for example, in an unconfined setting. We put all those together to come up with a drawdown, which gives us a lifting distance, and we can put all that together to come up with those pumping costs we were talking about. If it's a hypothetical well, we can optimize a screen for you, or if it's an existing well, we just take that. Excuse me, or if it's an existing well, we take that as a given input. All of those pumping costs together with these other relevant factors, we can put them together to come up with those limits we talked about just a second ago. The economic depth limit, the capacity depth limit, and if it's relevant, right, if we want to think about that, the desired future condition depth limit. And then again, using that yield calculation provided to us by total estimated recoverable storage, with these limits, we can come up with some yield numbers. The other way we work with this model is those socioeconomic impacts that we were talking about. And these are just for existing wells. And the approach is similar, but slightly different. Once again, we've got some similar inputs here. We don't need your willingness to pay or your storage area, right? Some other things like that. We do need all of those aquifer parameters that we're pulling from the Texas Water Development Board groundwater availability models. And now also what we do in this study is these items highlighted in blue, we get these from the submitted drillers report database, right? Your pumping rate, your what's the elevation of your depth and your well bore intervals, right, et cetera. And again, we put all that together to come up with some drawdown calculations and some lifting distances, and that gives us some pumping costs. Now, here, because we're only interested in socioeconomic impacts, we're not looking at capacity in the sense of calculating yields, but obviously we want to know if at some point the well fails to produce, right? I mean, you can't readily consider an economic impact if the well can't be pumped. So what we do there is we look at some remediation solutions. If the capacity of the well fails, what can we do to remediate it? Can we simply lower the depth of the pump all the way up to, can we drill into a deeper formation? Of course, those remediation impacts are also going to have pumping costs associated with them. So we put all that together. If we need to do remediation, we're looking at sort of a new well infrastructure. Once again, we'll optimize that screen interval for you. And all of that together gives us pumping costs at both the initial depth to water, whatever it might be, and that desired future condition depth to water, that new depth to water. Okay, so we talked about how we can approach this problem, right? How we can try to better quantify groundwater recoverability. Now we want to try to apply this to answer those latter two questions. And to do that, we're going to look at a specific study area to help test and develop the model itself. That study area for us is the Carrizo-Wilcox Aquifer, and specifically the footprint of the Post Oak Savannah Groundwater Conservation District. Why the Carrizo-Wilcox? Well, it's a critical and important resource, groundwater resource for the state. It stores, pursuant to TERS reports, about 5.2 billion with a B acre feet. That's about 45% of all major aquifer storage in Texas. And it's a lot of water. You know, as a kind of a quick reference point, it's over 50% of the volume of Lake Superior. And so that's what we've got pictured here down to the bottom left is the footprint of the Carrizo-Wilcox Aquifer. The solid red is the outcrop area, right, where the formations are at land surface, and the hatching indicates subcrop, where the aquifer is overlain by younger formations. And here to the right, I just have a quick stratigraphy to kind of help visualize this a little bit. We've got southwest, central, and northeast sections of the aquifer. And I've taken the liberty of highlighting the water-bearing formations in blue here. Sparta Sand, Queen City, these are minor aquifers of the state, so they're valuable and important, but they're not considered here. What we're looking at specifically in this study is the central section of the Carrizo, which is composed of 4 formations in order of decreasing depth. At the bottom, we've got the Hooper Formation, then the Simsboro, then the Calvert Bluff, and then the Carrizo Sand at the shallowest. Okay, so why Carrizo? Check. Why Post Oak Savannah Groundwater Conservation District? Well, perhaps most importantly, it gives us varied storage conditions to look at. Recall that one of our key questions here is we want to understand how do varied storage conditions impact recoverability. So because the Carrizo-Wilcox is down dip from northwest to southeast, within the Post Oak Savannah Groundwater Conservation District, here along the northwest terminator, we have the aquifer presenting sort of shallow and unconfined conditions, whereas down to the southeast, we have much deeper and confined conditions that we can test. There's also some interesting things going on in the Post Oak Savannah Groundwater Conservation District. The Vista Ridge Regional Supply Project, which provides water to the city of San Antonio, is pumping from within this district. The well field is right about here. And it pumps about 50,000 acre feet per year, which is, again, quite a bit of water. It's, about 3.6 times more water than all other uses in the district in 2013 combined. So, there's some potential water changes there, and we do see that, in fact, with the very recently adopted and finalized 2021 desired future conditions for this district. Those desired future conditions are anticipating and planning on an increase in the depth of water of all 4 of these formations in the Carrizo-Wilcox of between 50% and 109%. And that's what we have up here in the table to the right. Right. So, for example, in the Simsboro Formation, which is one of the more productive and more heavily exploited formations within the Carrizo-Wilcox, the 2010 depth to water on average throughout the district is about 256 feet from land surface. And the 2069 depth to water, again, if we assume that this depth to water change based on the desired future condition is on average throughout the district plus 278 feet, then it's going to come up to a 534-foot depth. So that's a change from 256 to 534 of 109%. The depth to water in the Simsboro is going to effectively double over this 50-year planning period. So with that kind of a change in depth to water, we could reasonably anticipate that there might be some interesting changes to recoverability worth studying here. Finally, the last reason that we chose to look at the Post Oak Savannah Groundwater Conservation District is they have a new, relatively new program called the Groundwater Well Assistance Program. And in a nutshell, what this program does is it says, if your well experiences a capacity failure, as depth to water changes in the region, increases in the region, then you are eligible to apply for some financing to remediate your well. But it has some limitations and stipulations that we'll talk a little bit more about in a minute. Okay, so now we've talked about how we're going to better quantify groundwater recoverability. We've talked about our study area that we're looking at. Now let's look at some results, right? First, how do groundwater storage conditions drive recoverability? So let's start off slow. Let's look at a single well, right? Using the groundwater recoverability model in a hypothetical unconfined setting and confined setting. The parameters we'll use here is a pumping rate of 70 gallons per minute and a willingness to pay of $100 per acre foot, storage area of a square mile, and a well screen, an arbitrary well screen of 40 feet, beginning 40 feet from the bottom of the aquifer. So there's some interesting things going on here that we can see. So in the unconfined setting, we see our capacity maximum depth to water occurs here, about 195 feet above the bottom of the aquifer. And this leaves us with a production range of 105 feet with a 300-foot saturated thickness with water levels imagined to be at land surface. What does that result in as a yield? Well, that's about 6,803 acre feet. There is no economic limit here because it occurs somewhere below this capacity maximum. On the other hand, when we look at the same aquifer, right, 300 saturated feet of saturated thickness, but with an additional 700 feet of pressure head above it, so a deep confined setting, we see that the capacity maximum depth to water occurs in the same place at the same depth within the saturated thickness. But now we have an economic maximum depth to water that's been introduced. At some point here, it was infeasible to economically continue pumping beyond this depth to water at a willingness to pay of $100 per acre foot. So here, the capacity maximum depth to water yield is pretty close to what it was in the unconfined setting. It's 7,475 acre feet, so a little bit less than an extra 1,000 acre feet produced from that pressure head, right? Again, with that storage coefficient being 3 orders of magnitude smaller, even though there's 700 feet of pressure head, the amount of water produced from that is only about 1,000 acre feet. But oh wait, when we look at the economic yield, right, what is the yield of water produced at this economic maximum depth to water, which is only 519 feet below land surface, well within the pressure head? Well, the amount of water produced there is actually only 498 acre feet. And again, why is that so much smaller than these yields, even though you're producing 519 feet of head, whereas this is only 105 feet of head? Well, again, it's that storage coefficient issue. And then finally, a quick note, we looked here at an arbitrary well screen interval, right? 40 feet, beginning 40 feet above the aquifer. If we use the groundwater recoverability model to optimize that well infrastructure, we can actually increase our capacity yields in the unconfined setting by 58% and in the confined setting by 53%. Okay, so single well, unconfined and confined setting. Now we want to look at a regional yield calculation. How are we going to do that? Well, we're going to imagine that we have a single well pumping within each 1 square mile of this aquifer footprint within this groundwater conservation district. We're going to use the same key parameters that we just used for a single well: 70 gallons per minute pumping rate, a willingness to pay of $100 per acre foot, cost of power 10 cents per kilowatt hour, well efficiency of 75%. And as we look at these next sets of results, I want you to keep in mind this red blob, right? This is the outcrop area of the Carrizo-Wilcox Aquifer within the Post-Oak Savannah Groundwater Conservation District. So these are those shallow and unconfined conditions. Down here, it's deep and confined. Just keep that shape in mind. Okay, so here's what the groundwater recoverability model tells us our optimized regional yields look like at the capacity limit. So this is imagining how much water could be produced if we drop water levels all the way to the point just before an optimized well fails to meet our pumping demand. So what we see, we've got some white cells here along the northwest terminator. Those are places where the saturated thickness, the potentiometric head available is insufficient to meet pumping demand without overpumping at those initial conditions. And then everything else is viable to produce. And what we see is, we've got yields ranging all the way from as little as about a 0.4 acre feet all the way up to over 110 acre feet. And what's interesting is, at this 70 gallons per minute pumping rate, we see yields that actually come pretty close to that 75% benchmark of total estimated recoverable storage. So, about 3/4 of the total storage in all 4 of these formations within this district are recoverable at the capacity limit for this pumping rate of 70 gallons per minute. Pretty good, pretty good. But what about the economic limits? Oh, well, that's a very different story. In total, we find that at the economic limits, where one is willing to pay $100 per acre foot, even at well infrastructure that's optimized to maximize this yield, we're only getting between 5 and 10% of our total storage, right? And I told you to remember that shape of that red blob. Remember that? Well, that correlates quite nicely with our hot colors and high yields, right, for each one of these formations within the aquifer. So what's going on here? Well, what this is showing you is that the the economic maximum depth to water that is feasible to recover water from in each one of these formations, where it's a hot color, that depth is falling within the saturated thickness of the aquifer. So you're getting that production from that specific yield storage coefficient. Whereas down here to the southeast, like we saw with that single well, the economic maximum depth to water is falling somewhere within the pressure head of the aquifer. So the yield that you're getting off from producing that water and draining the aquifer to that depth is from that confined storativity storage coefficient, which is 3 orders of magnitude smaller. Here's what we kind of just saw, but I just want to give you the chance to look at the same formation of the 2 different type yields side by side and standardized to the same legend. Right, so this is the Simsboro formation, again, one of the more productive and heavily exploited formations within the aquifer. On the left, this is the capacity yield, right? Again, 73% of total storage is feasible to produce. But on the right, the economic yield at $100 per acre foot, willingness to pay, only about 9% of the total storage is feasible to produce, and most all of that storage occurs along this area that is either unconfined or easily transitioned to an unconfined setting. Okay, well, so we wanted to know, how do storage conditions drive recoverability? Well, for capacity yields, what we find is that the saturated thickness of the aquifer itself is really the key driver of optimized yields. So here on the left, we've got that same figure, the capacity yield for the Simsboro formation, that's 73%. And here on the right, what we have is the saturated thickness of the aquifer. And you can immediately tell just visually, wow, this looks like almost the same graph, right? And what that's showing you is that it's really because the capacity yield is driven by the capacity maximum depth to water, and that depth to water falls within the saturated thickness of the aquifer. While you are getting some production down here from the confined pressure head, it pales in comparison to what's being produced by the saturated thickness. So saturated thickness is really the key driver here. And that's what this shows as well, sort of numerically. This is a cumulative distribution function. Here we've got in blue the saturated thickness, in red those capacity maximum depth water yields. And we can see that those track very, very, very closely to one another. By comparison, total head, right, which you might think might be a key driver, doesn't really actually track that closely, right? It's really, really driven by saturated thickness. Now, on the other hand, let's look at what's driving the economic yields. So here again, right, Simsboro formation, that economic yield, right, about 9% of total storage. What's driving that? Well, that's not as quickly, obvious just comparing these two graphs. But what it is, it's the depth of storage, right? And that goes back to the point I made just a moment ago about where the aquifer is in either unconfined or easily transitioned to confined settings. And so to help you visualize that, what I've done is I've overlain in gray the parts of the aquifer that are in a confined setting. And you can quickly see these hot colors, high yields, lie right along the unconfined setting, or in settings where there is it is confined, but the pressure head is very small and it's easily transitioned to an unconfined setting within the economic limits. And again, we have kind of the same thing pictured here numerically on the right. The red is those yields, and we see, oh wow, a whole bunch of yields in the region are quite small, right? These dark greens over here. And what we see that tracks closely together is the depth of the bottom of the aquifer, right? And the depth of that economic maximum depth to water. So again, the controlling factor for economic yields is the depth of storage. Okay, so we answered our second question about how do storage conditions drive recoverability. Now our last question, how do changes in recoverability impact our users? What are the socioeconomic impacts of desired future conditions? We can use the groundwater recoverability model, like we discussed, in sort of a similar way to answer this question. So here what we did for our study was we looked at the submitted drillers report database, and we found that there were about 450 wells within the Post Oak Savannah Groundwater Conservation District that are drilled into the Carrizo-Wilcox Aquifer. 84% of those are domestic wells, pictured in yellow. 11% were livestock wells, pictured in blue, and 5% were irrigation wells, pictured in green. And using the methods we talked about above, we calculated that pumping costs at the 2010 depth to water are about $253,000 per year, right? And that's what you see here in this pie chart. Of those costs, about 83%, right, about $211,000 was the cost of actually drilling the well in the first place. 4% of those costs, about $9,000, is the cost of the pump equipment itself. And about 13% of those costs, about $33,000, is the energy cost of lifting the water to land surface. So it's a couple of interesting things I just want to point out quickly. Even though irrigation, for example, is only 5% of our wells tested, you can see here that they're about 15% of the total cost incurred. And there's a similar story with livestock. It's only 11% of the wells tested, but it's about 15, 20% of the total cost incurred. Why is there an outsized cost borne by those two uses? Well, simply put, they pump more water than our domestic users do. So they're creating more drawdown, more lifting energy, bigger pumps necessary. Okay, so now we understand what the pumping costs were at the 2010 depth to water. We can use the same approach, adjust our depth to water pursuant to that desired future condition, and recalculate what our pumping costs will be there. Take the difference, and that gives us what the socioeconomic impact of the desired future condition will be. That's what we have pictured here. First, let's talk about those capacity failures and remediations that we mentioned previously. Of our 451 wells tested, we find that about 17% do not fail in any way. They don't require any remediation, whereas about 9%, so about 38 wells, fail and there's no remediation possible. They go dry. 74% of our 450 wells fail and require remediation that is possible, and the remediations applied, 70% of those simply required a deeper pump, and 30% of them required a deeper well to be drilled. Now, a quick note I want to mention here is that when we consider this change in depth of water of this desired future condition, we're imagining that every water level throughout the district is increasing uniformly. And that's not necessarily the case. The desired future conditions that we have reported are an average change in depth of water throughout the district. But with the data we have available, this is the assumption we make, that it's an average change that's uniform throughout the district. And that's the capacity failures and remedies that we see here. So when we think about those capacity remediations and the changes in pumping costs, right, what we find is that by the year 2069 in current dollars, there's an added $93,000 per year of pumping costs introduced by the change in depth to water under the desired future condition. And that's what we have pictured here in the various pie charts. Once again, we see that our livestock and our irrigation users are bearing an outsized proportion of those costs compared to the number of wells presented in the study area. And again, that's because they simply have higher pumping rates than our domestic users. But another key thing to think about is what the distribution of those changes in costs are. What we see here, right, of those $93,000 extra dollars per year by 2069, only 29% of those costs are drilling costs, whereas 56% of those costs are lifting energy costs. So I'm going to click back and forth. Keep your eye on this pie chart here, right? This is the added costs, and then the previous slide is the 2010 costs. You can see, just watch those percentages change, right? So what this means is that for this study area, the change in lifting energy costs, that's just the cost of power to lift the water to land surface, was actually far and away the majority change in socioeconomic impacts driven by the desired future condition. Now, by understanding this, we can learn a lot of things, right? And we can help manage these changes. So for example, I mentioned that the Groundwater Well Assistance Program that the Post Oak Savannah Groundwater Conservation District is running is intended to help offset some of these impacts to their users as the water levels change. But that program doesn't cover lifting energy costs. It only covers drilling costs, right? So the majority impact, socioeconomic impact driven by this desired future condition isn't being covered by this policy intervention. So there's potential lessons to be learned there, right? We could use information like this to perhaps better target policy interventions designed to offset these impacts. And of course, pursuant to our original question, here we can quantify the socioeconomic impact of the desired future condition. Okay, so let me just close and wrap up with just a couple minutes left here. What can we take away from this study? So groundwater recoverability, what is it? Well, it's a key element of groundwater availability, right? It's one of those many things that we should consider when we think about setting our desired future conditions, right? It's a function of the capacity of an aquifer and well to meet demand, as well as economic feasibility. What we did here in this study was to scientifically quantify it using our groundwater recoverability model. And in doing that, we found a few key things. One, that capacity falls with increasing depth to water, costs rise with increasing depth to water. And this method is directly compatible with depth to water based desired future conditions. Answering our second question about how storage conditions drive recoverability, we found that saturated thickness drives capacity constraints, and we found that the storage depth of the aquifer itself drives economic constraints. So in full closing, I want to reiterate that one size does not fit all. This was a difficulty, I think, of total estimated recoverable storage, was trying to come up with one number for everybody. In this method that we've developed here, results are highly subjective to use. A higher pumping rate is going to incur greater drawdown. Therefore, capacity yields will be smaller. Economic yields will be smaller because the cost associated with that higher pumping rate will be larger. Similarly, what one is willing to pay for the water will have a direct ramification for what is economically feasible to produce. Are you willing to pay $100 per acre foot or $500 per acre foot? All that said, even though this method does not create a one-size-fits-all solution, it can be used to quantify recoverability changes for known, estimated, or even potential uses. I want to reiterate that the model is designed to be applied to either existing well infrastructure that you specify, or it can optimize it. It can do that for a single well. It can do that for a region. And that optimized infrastructure, how can we optimize it? Well, we can optimize it to maximize your recoverable yields. Or, for example, if you're looking at a desired future condition, depth to water, we can optimize your well infrastructure to minimize your recovery costs within that depth to water change. And altogether, we can use this data to evaluate threats and opportunities. We can estimate how costs will change for, say, a domestic user or an alfalfa farmer. We can, of course, pursuant to our third question, determine what socioeconomic impacts are expected to occur under a desired future condition. And then, as that last point we talked about with the Groundwater Well Assistance Program, we can use that data to help better guide our policy interventions to achieve the maximum intended effect. Okay, so that kind of wraps up. Let me just do some acknowledgements. It's critical, right? This work would not be possible without everybody you see on this screen. I mentioned that this is a dissertation research conducted at UT. Dr. Michael Young, who's with us here today, was my supervisor. Dr. Sheila Olmstead, Daniela Rempe, and Jay Banner were on my committee. And then, of course, I was supported by the Jackson School of Geosciences at UT, the Bureau of Economic Geology at UT, the State of Texas Advanced Oil and Gas Resource Recovery, or STAR program, Planet Texas 2050, the Bureau of Economic Geology Excellence Fund for Water Research and Policy, and then most recently, the Texas Water Resources Institute. And with that, I thank you again so much for giving us your lunch hour. I really appreciate it, and I'm happy to answer any questions you might have.